Imagine, it is 1921. You have a son, aged 14, and he comes to you one morning complaining of the strangest symptoms: blurry vision, frequent urination, much more than is normal for a child his age. He's also lost a considerable amount of body weight, and he literally looks like a walking skeleton. No amount of eating can help him gain back the weight he's lost. So you decide to take him to a hospital, do a routine checkup on him. And there the doctors inform you of the worst possible news. Your son has diabetes. He only has another month to live. In the early 20th century, diabetes was a death sentence. Children with diabetes rarely live longer than a few months after diagnosis, whether they're 14 years old or 14 weeks old. The tragedy and the horrors that came with this illness, though rare, was a common reality for any parent of a diabetic child. There was one such child in 1921 who had diabetes. His name was Leonard Thompson. And just like our hypothetical boy we imagined, Leonard Thompson also had a lease on life, and he was running out of time. On January 11th, 1922, a scientist named Frederick Banting performed an experiment on Leonard Thompson, the first ever of its kind. He was days away from death, but Frederick Banting took a pancreatic fluid from a dog and injected it into the diabetic child. And a few hours later, he was healthy again. The thing that Banting used to save this child's life was called insulin. Today, with regular insulin therapy, we have extended the life expectancy of children from 14 years to 65 years. And now in this age of 2016, with glucose monitoring, insulin injections, insulin pumps, we have actually managed to increase the lifespan of diabetics. But frustratingly, we haven't knocked it out for good. In this era, is there a better, more modern solution for diabetes? Turns out, in order to cure diabetes, you have to get a diabetic to produce their own insulin. In healthy individuals, these beta cells are working fine. They can produce the insulin, release the insulin, and your body responds very well to the insulin. But in a diabetic, that's not the case. Either your body doesn't respond to the insulin, or your beta cells are sick or dying. So to cure diabetes, it isn't enough to just shove beta cells into an individual and hope for the best. You actually have to transplant healthy beta cells that have the ability to work together and communicate with each other in a normal fashion. And this crosstalk is absolutely essential for the beta cells to keep you healthy. So how does this communication work? Well, it works in kind of the same way construction builders build seaports. Imagine this: a cruise ship going from city to city, picking up and dropping off passengers along the way. But it's not able to go to its destination without a seaport or a functioning dock. And that's one important thing that a cruise ship absolutely needs in order to pick up passengers. The dock has to grab onto a cruise ship, keep it there in place, and prevent it from floating out to sea. Now, of course, you need something to keep your dock from floating out to sea too, and this is the support infrastructure for your dock. Literally, you need beams or anchoring points to keep the dock stationary, stuck to the ground so it doesn't float away. In the normal sequence of events, you have to build your support infrastructure, and then you build your dock. Once the dock is constructed, a cruise ship can come in, bind to the dock, and allow passengers to come aboard. And once the passengers are aboard, the cruise ship can leave and go to its next destination. In the normal sequence of events, you build your infrastructure, the support beams, then you build your dock. And once the dock is constructed, now the cruise ship can bind to the dock, allow passengers to come aboard, and the cruise ship can get released and go to its next destination. It turns out beta cells operate analogously. Just like construction workers working together to build docks and seaports and infrastructure, beta cells come together and they build the docking mechanism for insulin molecules. When two beta cells come into contact, there are proteins on the surface of beta cells that act as the anchoring point for the dock. And then, of course, there are proteins inside the beta cells that form the docking structure of the dock itself. And then once this entire apparatus is constructed, now the insulin, or the cruise ship, can attach to the dock. And once the beta cell is ready, it will be able to release this insulin much more effectively and release a lot more insulin once the dock is finally constructed. There are hundreds of proteins expressed on the surface of beta cells, and we only know how a few of them work in terms of insulin secretion and insulin production. This is where my research comes in. There are literally hundreds of proteins on the surface of beta cells, but we only know how a few of them work. I'm trying to figure out how the rest of them work. We can study this by removing proteins from the surface of beta cells and seeing what happens to the beta cells' dock and release function. Is it able to secrete more insulin or less insulin? So far, we found that some of these proteins tell the beta cell to make more insulin. Other proteins tell the beta cell to make more docks. Some proteins even give contradictory orders. Make more docks, but don't release the insulin. So what does this mean in terms of treating diabetes? Well, we can use the right protein combination to enhance a beta cell's normal function. But in terms of a diabetic that doesn't have any beta cells left, well, we can transplant healthy beta cells with this right protein combination so that it can produce insulin for the diabetic. In this way, diabetics can rely more on their natural insulin than insulin from injections. I want to see a future where a child complaining of the strangest symptoms comes in for a hospital visit and the doctor says, "You have diabetes, but don't worry, we can fix your beta cells so you won't have diabetes anymore."